Hello everyone, today we're talking about linearly independent sets and bases. This is material from 4.3 of your textbook. So we're going to talk about some notions that we've already seen in the context of vectors in Rn, and we'll say a little bit about how to generalize that to arbitrary vector spaces, and we'll talk about the important definition of a basis. That's our main kind of goal for this lecture. So suppose V is a vector space. So remember, one example of this is vectors in Rn, like R5, but we also have these abstract vector spaces that are like polynomials of degree at most 3, say, or something like that. So here's a definition. A collection of vectors, let's say V1 through Vp, we say this is linearly independent. The collection is linearly independent if the vector equation, so what's a vector equation? That's C1 V1 plus C2 V2 plus ... CP Vp equals 0, has only the trivial solution, C1 equals 0, C2 equals 0, ... CP equals 0. So just to remind you guys that, when we're talking about an arbitrary vector space, we can talk about linear combinations because we can take a vector and scale, and we can then add up all of those scaled vectors. And we want to say, we have a vector equation when we set that linear combination equal to 0. There's always a way to solve this guy if I make C1 0, C2 0, etc. And if that's the only way to get the 0 vector, we say it's a linearly independent collection. So the first theorem that's going to be maybe familiar to us from the context of vectors in Rn is that a collection V1 through Vp is linearly dependent So linearly dependent, of course, means not linearly independent. So dependent if and only if some vector, say Vj in that collection, well, let's say j bigger than 1, is a linear combination of the preceding vectors. Okay, so remember that this doesn't mean that all the vectors can be written as a linear combination of the preceding, but there's going to be some guy, some Vj in this collection where I can write it as the linear combination of the previous. That's the same as saying that the collection is dependent. So let me give you an example here. Let's go to our abstract world. So e.g., let's take V to be P, I don't know, let's say P2. This is the polynomials of degree at most 2. And let me take a collection, let's say P1 is the vector 1, P2 is the vector, say, t, P3 is the vector 4 minus t. So I'm thinking about these polynomials where the variable is t. I think sometimes we call them x, but, well, today we're calling them t. And I claim then the set P1, P2, P3 is linearly dependent, so not independent, since I can write, how do I write the 0 vector as a linear combination of these guys? Well, what's the 0 vector? That's just the 0 polynomial here, 0 plus 0t plus 0t squared. And I can write that as, let's see, I want to take 4 times P1, and then let's take plus, well, I'll say minus 1P2, and then I'll take minus P3, What do I get here? Well, 4P1 is just 4, and then I get minus P2, which is t, minus 4 minus t, which is P3, and if you check, this equals 0. If I did that right, it looks good. And of course, you notice that I can write the vector P3, which is 4 minus t, of course, as 4 times P1 minus P2. So you see that I can write this vector P3 as a linear combination of the others. That means that this collection is dependent. That's the same thing as saying that I can write the 0 vector as a linear combination of the vectors you gave me. Okay, so here's our next main definition of the day. This is our most important definition of this chapter. So maybe I'll give you the definition and then we'll talk about kind of why it's important. So suppose H is a subspace of a vector space V. Remember, subspace is this subset of a vector space that's closed under the two operations of addition and scaling. Then a collection of vectors, say B, which is B1 through, say, BP, collection of vectors is a basis for H if two things happen. So what we have here is we have, H is a subspace of V. Sometimes we think of H as actually just equal to V. So if you want, just think of, this is the subspace, this is the vector space. Then a collection is going to be a few vectors that satisfy two properties. So first of all, the collection B should be linearly independent, which we just talked about, what that means. So this collection of vectors better be linearly independent. And then the other important feature is that H equals the span of those vectors in the collection. So remember, what does span mean? That means all possible linear combinations. So another way to say this, that this H should equal the span of B, is to say that every vector in H can be written as a linear combination of the vectors in B. That's the same thing as saying that H equals the span of B. Okay, so I think I'll end it here. So this is the main definition of the day, that what a basis is. In the next lecture, I'll talk about a couple examples, and I'll maybe give you a reason why we care about these. Maybe it seems like a funny definition, but we'll see that bases are an important part of linear algebra. It's actually something we've kind of studied in the background already. But that's it for now, so we'll see you soon.